Hello and welcome back to my channel. Today we're going to be talking about the integral test or the integral test for convergence. So, if f is positive, continuous, and decreasing for x greater than or equal to m, where m is a positive integer greater than or equal to 1, then a sub n equals f of x. Or and a sub n equals f of x, then the summation from n equals 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx either both converge or both diverge. So realistically, what we are going to be doing is, as long as our series fits it being positive, continuous, and decreasing, then we're going to use an improper integral to decide if our function, our series, is converging or diverging. Because if one converges, then the other does. So we have our three conditions that we need to show in order to use this test. Those three things are: the function is positive, it's continuous, and it's decreasing. So one of the things to keep in mind is that we're only looking at these functions as functions from n to infinity, not necessarily, or 1 to infinity, and we're not really looking at negative values. So sometimes when these functions are going to not be continuous at 0 or at certain places, it's not a big deal for what we're doing. So we're going to look at this first one. We have the summation from n equals 1 to infinity of n divided by n squared plus 1. We're trying to decide if it converges or diverges. So last time we talked about the nth term test for divergence. We would take the limit as n approaches infinity, and if it did not equal 0, then we knew that it diverged. If we look here, this would be a limit that goes to 0, so we wouldn't necessarily know converges or diverges. It's not in any of the forms that we need so far, so we have to try something else, and our something else is this integral test. So we need to make sure that we show those three things in order to use the integral test. So the first thing that we're going to do is we're going to let a sub n equal f of x. And what we mean by that is we're going to take that n over n squared plus 1 and we're going to change it to x over x squared plus 1. It's the same thing, just with x's. So what we want to do is make sure that it's positive. So 1, it's positive. The denominator is always going to be positive because we have x squared. So something squared plus 1 is always going to be positive. The numerator is positive when we're looking at positive values. Thankfully, we're only looking at values greater than or equal to 1. So we can look at this and just say f of x is positive for x greater than or equal to 1. Okay, continuous. So it would be not continuous or discontinuous if the denominator would equal 0. If we look here, this would give us 0 is equal to x squared plus 1. X squared plus 1 is never going to equal 0. It's always going to be a little bit more than 0. So f of x is also continuous. For x greater than or equal to 1. Our last one is decreasing. So in order to talk about decreasing, we are going to be looking at the derivative of our function. So first thing we want to do is find the derivative of what we have. So in order to do that, we need to use quotient rule. So u prime v minus v prime u divided by v squared. So u prime times v minus v prime times u all divided by v squared. So x squared plus 1 minus 2x squared x squared plus 1 squared. This gives us 1 minus x squared divided by x squared plus 1 squared. And when we look at this, the denominator is always going to be positive because we're squaring it. X squared in itself is always going to be positive, but because we are subtracting it, 1 minus x squared, 1 minus x squared is always going to give us something that's negative as long as we are bigger than 1. So we are decreasing f prime of x is less than 0 when x is greater than 1. So we are positive, continuous, and decreasing, which means the integral test can be applied. Okay, so now what we're doing is we are looking at the integral from 1 to infinity of x divided by x squared plus 1 dx. So now we're going to do our improper integral. So we're going to take the limit as b approaches infinity, and we're going to replace that infinity that we had in our integral with b. And that is going to be of x divided by x squared plus 1 dx. And then we're going to go ahead and integrate what we have. So we are going to integrate this. X squared plus 1 is really close to what we would need. So we would technically use u substitution here, where u would be x squared plus 1, du would be 2x. But we don't have the 2, so we would bring the 1/2 over here. So we can use the same idea to kind of help us out here by adding in this 1/2, but also adding in the 2 into the numerator. So what we're really looking at here is 1/2 the integral from 1 to b of 2x over x squared plus 1 dx. So now having the 2x over x squared plus 1, this is giving us the exact form we need, and we have that 1/2 out front. So we have the limit as b approaches infinity of 1/2. The integral of this is the natural log of the absolute value of the denominator, so x squared plus 1. And we're going to evaluate that from 1 to b. So we have the limit as b approaches infinity of 1/2 times I'm going to bring that 1/2 out front, so we just plug in what we need. So we have the natural log of the absolute value of b squared plus 1 minus the natural log of the absolute value of 1 squared plus 1. Okay, so b squared plus 1 natural log, this is still going to be our natural log function, and as our natural log function goes on forever, it's going to still increase even if it's little by little. So this right here is going to go towards infinity. This is going to go towards the natural log of the absolute value of 2, but the infinity really just trumps all of it, so we know that we're going to be diverging. So what this tells me is this series diverges because the improper integral diverges.